All right, welcome back. We are moving on to Unit 7, and this unit we're going to be talking about actually two different topics. One is the exponential function, and the other one is the logarithmic functions. So we're going to split into two pieces, right? Two parts. We'll first talk about exponential functions. Okay, so we are going to be analyzing and transforming exponential functions. So we are going to be moving sideways, up and down, expanding, compressing, just like what we did in Unit 3 or Unit 4 rather. Okay, so here let's first talk about what is an exponential function. Okay, so an exponential function. Is any function of x that can be written in the form y equals or f of x equals to k, which is the constant base. Okay, that's the base to the power of x. So the key is that the variable is where the exponent is. Okay, so y equals f of x, or if you write it in the function notation form, f of x is equal to k to the power of x, where k is a positive constant. Okay, k cannot equal to 1, but it's positive, so it could be 1.5, it could be 0.2. Okay, it doesn't have to be a whole number. But it could be anything that's positive. Not 0, right? 0, remember, is not a positive number. And x is simply any real number. So here you can see if y is equal to k to the power of x, and if the constant, the base, is bigger than 1, this is what the exponential function look like. It's actually increasing. Okay? Whereas if the constant, if the base is between 0 and 1, it looks like this. And this is what we call an exponential decay, right? So this is called exponential decay. So I'm sure you probably heard of this in science. Exponential decay, because it's decreasing, right? As again, x increases. We always look from left to right when we graph. This is what we call the exponential growth. Exponential growth. Okay, so one is increasing, one is decreasing, and that depends on the base. If the base is between 0 and 1, it's a decay. If it's bigger than 1, it's growth. Okay, so here it says when k is bigger than 1, I jumped the gun there. When the k is greater than 1, it is an exponential growth. When k is between 0 and 1, and as x increases, y decreases, and approaches 0, it is an exponential decay. Okay. So let's take a look at some characteristics of the exponential function here. It says an exponential function, y equals to the k to the power of x, where k is bigger than 0 and not equal to 1, has the following characteristics. So if you look at these two graphs, okay, of course, these two graphs, the one right here, these two graphs, they have not been transformed at all, right? But let's look at the basic exponential graph, and then we're going to transform from there, okay? So for the basic exponential graph, whether it's growth or decay, doesn't matter. It always has an y-intercept at 1, right? The y-intercept is always at 1, right here and right here. So the y-intercept is always at 1. It has a horizontal asymptote, right? This is your horizontal asymptote right here. This is your horizontal asymptote right there. And the equation is y equal to 0. It does not have x-intercept, right? Because that's your asymptote right there. Okay, so it does not. Again, this is only true for k to the power of x. Of course, once you move the graph around, these are going to change. But these are the basic characteristics, or these are the characteristics of the basic exponential function. So the domain for the exponential function is actually all real numbers. There's no restriction for your x, for your domain. However, for the range, because we do have an asymptote at y equal to 0, so the range is actually at y is greater than 0, not equal to 0. Okay, it does not equal to 0. It never hits 0. It gets closer and closer to it, but it will never be 0. Okay, so let's take a look. Let's use one example here. Let's say the base in this case is 2. So we're gonna graph, and we're gonna figure out these information here. So I'm just gonna use table of values for now, because that's always a way to graph. And we can use any x value, so I'll just go from -1 and go to +2, maybe. -1, 0, 1, and 2. And for the y value, it is simply going to be 2 to the power of -1, right? So if you recall, 2 to the power of negative 1 is equal to 1 over 2 to the power of 1, which is 1 over 2. So that's 0.5. Okay, 2 to the power of 0, anything to the power of 0 is 1. So that's 1. 2 to the power of 1 is 2. 2 squared is 4. So now we can plot these points. So negative 1 and 0.5, that's 1 right here. So 0.5 somewhere here. Y-intercept of 1, again, that's the characteristic that we found earlier. 1 comma 2, 2 comma 4. So here really is our exponential function right here. Looks like this. Okay. So let's figure out the characteristics here for y equals to the power of x. The intercepts, again, we do not have x-intercept here. We do have y-intercept, which is at 1. Okay, that does not change. Asymptote, again, that does not change. It's y equal to 0. That's our horizontal asymptote right here. Okay, this is, I'm going to write down HA actually. Okay, so this, we do have a horizontal asymptote, and the equation is y equal to 0. Domain and range, well, domain does not change. It's still all real numbers, and range is still y is greater than 0. Is this increasing or decreasing? Well, I think clearly from the graph, this is an increasing graph. Okay, this is exponential growth. And again, you can tell based on the base. Right? The base here is bigger than 1, therefore this graph is going to increase. Okay, so this is the basic exponential function. Now we are going to take one step further and we're going to transform it. Okay, so let's go to the next page. And before we look at this monster right here, let's look at our what we did in unit 4. Okay, so here is y equals to f of x, or whichever unit it was. I can't remember. It's the transformation one. I think it's unit 4. Could be 3. I don't remember. Okay, the general form of a transformation done to the function y equals to f of x. Remember, it was the ABCD. So it was a times f bracket b of x. Oh, sorry, b of x minus c, close the bracket, and plus d. So this was in general, right, for any function. Now recall, a tells us the vertical expansion or compression, and whether there's a reflection over the x-axis. Okay, so that depends on whether a is positive or negative. So this one, okay, and b is the horizontal expansion or compression, and whether it reflects over the y-axis. Okay, depending on whether b is positive or negative. C tells us whether it moves to the right or left, and D tells us whether it moves up or down. So same thing actually can be applied to the exponential function. Okay, so here this is the basic exponential function. We can still apply the ABCDs to our exponential function, and you know, the way it works for ABCDs for any general function would actually work for exponential function too. Okay, so we do have the A here. B again is in front of x, and we have C is after the x, and D is outside of the function, right? You can see this is the function, so A is in front of the entire function, right, in the front, and D is added after k to the power of x, and again B is in front of x, and C is right after x, just like what we have here. Okay, so if you recall, again, I just mentioned earlier, A is the value that tells us whether it compresses or expands vertically. So the factor is simply A. I'm going to say absolute value of A. So if A, if you don't remember, if A was bigger than 1, it's a vertical expansion. If A is between 0 and 1, it's compression. Okay. Horizontally, the factor would be the absolute value of 1 over B. Okay, 1 over B. So if B is, let's say, 0.5, in that case, the factor, it's going to be 1 over 0.5, which is 2. So that would be a horizontal expansion. Whereas if B is, let's say, 2, then it would be 1 over 2. So that means horizontal compression by half. Reflected in the x-axis, so I was just mentioned about that. That would be when A is less than 0. We would have a reflection in the y-axis when B is less than 0. We would have translation of D units vertically. So if D is positive, we move up. If D is negative, we move down. We would have the translation of C units horizontally, same thing. If C is positive, we move to the right. C is negative, move to the left. Okay, now if you recall, the point xy on y to the power of y equals k to the power of x corresponds to these 2 points on the transformed form of the exponential function x over b plus c and ay plus d for the new y value. Okay, so we're going to take the graph that we had in the previous page and we're going to sketch this. Okay, so recall I'm just going to rewrite the table of values here. This was 0.5, this was 1, 2, and 4. Now we are going to have, so I'm going to write down the values of a, b, and c, and d. Now recall, we always factor out the value of b, so this should be rewritten as 3 times 2 to the power of negative of x minus 2. Okay, so you should always factor out the value of b right there, which is in this case negative 1. Okay, so now we can see a is equal to 3, b is negative 1, and c is, be careful, it's actually positive 2, not negative 2, right? It's x minus c, so if c is 2, then it's just x minus 2, okay? Or there's no value of d is just 0. Okay, so that means, recall these two pair together and b and c goes together. That means our new x value, I'm going to use red color, okay? So we would have the following new coordinates. So for the x value, recall it's gonna be x over b plus c. So it's gonna be negative 1. I'll do it for one number. Negative 1 over b, which is negative 1, plus the value of c, which is 2. So negative 1 divided by negative 1 is 1. 1 plus 2 is 3. Okay. So I'm just gonna do that for the rest of these 3 x values. That's gonna be a 2. 1 divided by negative 1 is negative 1, plus 2 is now 1. And this is going to be 0. For the y values, it's going to be ay plus d, as it states right here. So, well, d is 0, so really we just need to multiply the old y value, the original y values, by 3. So 3 times 0.5 is 3 times 0.5, which is 1.5. 3 times 1, 3 times 2, 3 times 4. Okay, so now we can use this table of values and then we can graph. 3, 1.5, 1, 2, 3. 1.5 is right here. We have 2, 3, 1, 2, 3. 1, 6, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 right here. Okay, now there's one more thing I would like to mention. In the original graph, recall there was a horizontal asymptote y equal to 0. Right? So that's that. Now this will change if there is a vertical translation. However, we do not have a vertical translation, so actually it remains the same. Okay, so our horizontal asymptote remains right here. Again, our horizontal asymptote will shift up or down depending on the value of d, because the value of d here is 0, so it actually does not change. So if we just join the points in the curve, there is our exponential function right there, or the graph for the exponential function right there. Okay, so now we can write down or figure out the information here. The intercepts, well, again, because our horizontal asymptote does not move, we still do not have x-intercept. But we do have y-intercept, and it is now at 12. The asymptotes, okay, I just mentioned right there, the horizontal asymptote is y equal to 0. So I guess that's part B. C, domain and range. Domain does not change because it was all real numbers, so no matter what you do to your function, it's not going to change your domain. Range, in this case, does not change either because we did not move the asymptote. Okay, so hopefully that was okay for you. Yeah, just get your original table of values, apply the ABCDs and the transformations, then you get your new table of values, then you can plot them. Okay, so I will let you try this one and see how you do. Good luck. Okay, so hopefully the first step that you did was you factor out the negative 2 right here, and you should end up with x minus 1 and then minus 3. So now I can figure out my ABCDs. A is actually negative 1, B is negative 2, C is 1, and d is -3. Again, a and d go together, b and c goes together, right? It's x over b plus c and ay plus d. Let me just write that down here. X over b plus c and ay plus d. Okay, now it says it's the y equals to 3 to the power of x. So what we need to do first is to get a table of values for that. And for exponential functions, really I just need to see 3 points. Okay, these three. Okay, 3 to the power of -1 is 1 over 3. 3 to the power of 0 is 1. 3 to the power of 1 is 3. I mean, if you wanted to, you can add one more, 2 comma 9. Okay, and this again would have horizontal asymptote y equals 0. All right, I will use green to draw this. Okay, so now it's going to be x over b plus c, so it's going to be -1 over the b value, which was -2, plus c, which is +1. Okay, so that's what you need to do for the rest of the x values. So that's 0.5 plus 1, that's 1.5. That's 1. This is going to be 0.5. Yes, and then this is going to be, well, 2, that would be 0. Okay, now for the y values, it's ay plus d. So it's going to be, what's the value of a? -1. So -1 times the original y value plus the value of d, which is -3. So -1 times 1/3 is -3 minus 3. This is going to be -3.3 repeating. And then we have 1, -1 times 1. And then -3, that's -4. And if you just keep going, this is going to be -6. This is going to be way too small or too negative. Okay, I'll write it down as -30. It's not really going to be in our graph. That's okay. We do have new horizontal asymptote, right? Because we do have the value of d. We are moving the entire graph down by 3, so the horizontal asymptote is not going to be at y equals -3. So I'm going to draw that horizontal asymptote right away, actually. Okay, and now I can plot the rest of the points. 1.5, comma 3.3, right here. Oops. 1, comma -4, 0.5, comma -6, 0, comma -30 is somewhere actually quite down there, something like this. And here is my, okay, again, that's my asymptote. So again, my graph will go towards it, but it will not cross it. Okay, so now we can figure out the information here. The intercept, well, you can see we still do not have horizontal asymptote based on the graph. We do have the y-intercept, which is at, what is it? It's at -30. If you didn't do the last point, you can still figure out the y-intercept by simply plugging 0 into this equation right here. Okay, so you can always find the y-intercept by plugging 0 into x. So what I mean is this: you can say -3 to the power of -2 times 0 plus 2, and then minus 3. You should get negative of 3 to the power of 2 minus 3, which is -27 minus 3. That's -30. Okay, same result. Okay, asymptote. Here's my asymptote right here. Part C, domain and range. Domain again does not change, it's all real numbers. Range will change. In this case, it's now less than -3. You can see the graph is actually underneath the horizontal asymptote. Okay, so again, a little bit of review of what we did in the transformation unit, and I guess apply to the exponential function. So really, what you need to do is this first, right? Get your original table value for the exponential function, and then apply the transformation techniques that we learned earlier. Okay, so here we go. Last example here is as using transformation of exponential functions to model real-world situations. Okay, so we have, it says for every meter below surface of water, the light intensity is reduced by 2.5%. The percent P of light remaining at the depth d meters can be modeled by the function P is equal to 100 times 0.975 to the power of d. Now, this case, it says graph the function for the depth between 0 and 40. Now we're going to use decimals to graph this because, I mean, the base is not a nice number. We don't really want to graph this by hand, okay? So what you need to do is take out your phone, I guess, or computer, and you can go to decimals, and you just need to type out the function. It was 100 times 0.975. In a second, I'll explain to you why it is 0.975 to the power of x. I guess I probably need to type in y equals, okay? And it says you want the domain to be between 0 and 40. So what you need to do is you click on graph setting. You need to change the x-axis to go from, I wouldn't actually use 0. I probably go from -5. And again, I won't go to 40 only. I probably go to 45. Okay, and that's that. You cannot see anything from your graph. Okay, so what you need to do is well, I guess you can just zoom in. Okay. I do believe though you can actually, oh, what happened there? Okay. Okay, so indeed you can actually restrict the domain on decimals. What you need to do is you type in the function, and then you put curly brackets right after the function, and then you can set the domain that you wanted. And there is our graph right there, okay, with domain between 0 and 40. Okay, so now that's part A. Now I mentioned earlier I want to kind of explain to you why this function works. This 100, okay, the number 100 right here, this represents 100% of the light intensity, okay, right, at the beginning, right, when the depth is 0 on the surface of water, right, so the intensity of light is actually 100% right there. The 0.975, because it's reduced by 2.5%, so it's 1 minus 0.025. Right? So this is actually the base. For every meters goes down to the water or down into the water, it reduces 2.5%. So it's only 97.5% left of what it was, right? And that's why the base is 0.975. Okay, so part A we did it. We graphed the function. Part B says to the nearest percent how much light remains at the depth of 10 meters. So this is easy. All we need to do is we simply plug in numbers because it tells us the depth is 10. So we simply plug in 10 into the D, and then we put this into a calculator. That's what I'm going to do right now. 0.975 to the power of 10 times 100. This is going to be to the nearest percent. So I guess we would have, it is actually 77.6. So if you round it to the nearest percent, that's going to be 78%. Okay, so if you go down 10 meters under water, below surface of water, the light intensity will reduce to only 78%. Okay, part C, it says to the nearest meter, what is the depth when there's only 50% of the light remains? So then what we need to do is this is our equation. 50 is equal to 100 times 0.975 to the power of D. Okay, we don't know how to solve this exponential function equations yet. We haven't learned that yet. I will show you later on in this unit. But for now, what we need to do is we need to go back to the graph. And so there is my graph, right? This is my function. And what I need to do is I need to set a second equation, y equals 50. And, right, so that's when this point right here is where they meet. This point right there, that's where they meet. And therefore, that's the point of intersection. And so that's the solution. So if you just double click at that point, you can see, remember our y-axis our x-axis represent the depth, and the y-axis represents the intensity of light. So when the depth is 27.378 meters below the surface of water, the light intensity reduced to 50%. Okay, so I guess that's the answer to the nearest meter. In that case, it's going to be 27 meters. So D would be 27 meters. Because again, if you look back, it's 27.378. We will just round that to 27 meters. Okay, so that's the graphing. That's the question that you need to be able to solve graphically. Okay, we will actually learn how to solve it algebraically as well. Okay, so here's the last, I guess, kind of practice question. It says, given the function y equals to k to the power of x, write the equation of the image graph after the following transformation. Okay, so these 5 transformations all apply to the y to the y equals k to the power of x. Okay, so it's one question, not 5 questions. It's just one single question, but there are 5 different transformations. So give that a try, and I'll show you the answer in a bit. Okay, so it says vertically compressed by factor of 0.25. That means A is 0.25. It says horizontally compressed by factor of 0.5. This means B is equal to 1 divided by 0.5, which is 2. Translate 4 units to the left, okay, -4. So 4 units left, that means C is -4. Vertically, 4 units down, so that's D is -4. Reflected in the y-axis, that means y-axis is this one, so that means x becomes negative, or positive to negative, negative positive. That means b is less than 0. So recall it was y equals a times k to the power of b times x minus c plus d at the end. So our value of a is 0.25. K is simply k. B is now -2. Okay, it's not just 2 because b is negative. And then x minus c, c is -4, so it's going to be x plus 4. Plus d, d is -4, so -4. And there is the new transformed, or there's the equation of the transformed graph. Okay, that's it. Let me know if you need some help. Otherwise, that's it for this lesson. Yeah, try some questions on your own and let me know if you need help. Okay, good luck.